In a climatological assessment of intense extratropical cyclones from the potential vorticity perspective, Seiler aimed to present a climatological assessment of how surface temperature, condensational heating, and stratospheric intrusion affects extratropical cyclone development and intensification. And this was done by using a potential vorticity inversion technique. And so extratropical cyclones are important as they exchange moisture, heat, and momentum between the tropics and the high latitudes. And the contributions of these perturbations in potential temperature and potential vorticity to the extratropical cyclone intensification involve potential temperature anomalies near the surface, lower atmospheric condensational heating, and upper level stratospheric intrusion. And so for this paper, the cyclone tracking was accomplished by using 6 hourly horizontal wind speeds at 850 hectopascal for the calculation of relative vorticity at this level, retaining only storms that had this relative vorticity greater than 10 to the minus 5 per second, with intense storms at 10 times 10 to the minus 5 per second, but these storms had to have lasted longer than 2 days, travelled at least 1,000 kilometres, and they have to have been between the period of 1980 to 2016 for 30 degrees north to 72 degrees north. And so the piecewise potential vorticity inversion allows the partitioning of PV perturbations into layers with the use of relative humidity to allow the computation of those separate driving variables previously mentioned. And this piecewise potential vorticity inversion technique can be seen in Figure 1, where you take your air temperature, zonal meridional wind speeds, and geopotential height. You can process it into separate components of PV, stream function, and geopotential, and you can partition PV perturbations into layers. And the advantage is that Ertl PV can be converted to recover geopotential and stream function, so we can quantify perturbations of these two things at each level that contributes to the perturbation of PV during intensification. And so this is the visual representation of that process. And so the results. The vast majority of the extratropical cyclones in this study were ones that travel across the North Pacific and North Atlantic during the cold season. They were the intense ones. What you see in Figure 2 is that the upper level and surface, the upper level contribution, and similarly for the surface, provided a much lower representation to the total relative vorticity for the cyclones due to the PV perturbations. So the lower level had the most significant impact on that variable seen in Figure 2a. Most of the extratropical cyclones were mainly driven by condensational heating, but I think the main and most interesting conclusions from this study is that Figure 3 shows that the extratropical cyclones that occurred in the North Pacific and the North Atlantic had higher contributions from the lower level condensational heating, and that these were the ones that were dominated by the condensational heating, which shown within figures 3 and 4 here. And also those dominated by lower level condensational heating also occurred in warmer months, with those by potential temperature anomalies occurring in the colder months. And so the limitation is that the results of the frequencies was in figures 3 and 4 applies only at peak intensity, and that PPVI is not applicable during the early stages of development, which may cause an underestimation of upper level and surface contributions. And so future work may involve assessing whether strong contributions from potential temperature anomalies in the cold season were due to the temperature differences between the surface and the air, or if the high frequency of events dominated by low level condensational heating in the warmer months can be explained by Clausius-Clapeyron, with the importance of this study in bias correction in global climate models to do with latent heat release and cyclone intensity.